All right. It's not working. All right. So I'm just going to go through some brief things, just about a little bit more on hydrothermal alteration. Lucky you guys, must be sick of it by now. This shouldn't take long. These are just some of the textural features. A lot of them you probably can tell are fairly self-obvious from the stuff we've gone through, but they do give us an indication of sort of how these things have come about and a little bit about phase diagrams. So the textures of the alteration will give us an idea about what deposition mechanism is going on, timing relationships like we've done in your assignment, potential mineral assemblages associated with the ore deposit, which is what we see, and relationships or evolution in temperature, pressure, pH, redox, blah, 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 etc. So one of the most common ones, and this is not just alteration, in metamorphism as well, is a thing called pseudomorphing. So fancy word to say something that takes the form of something else. So morph being form and pseudo meaning a false form, if you like, or false. So it mimics the relic phase. So it could be a rectangular form that's an original feldspar, but it's now a new mineral. That's what a pseudomorph is. Here's an example of wollastonite. It's taking on the form of calcite. So that's a pseudomorph. If it's like cerussite, it's going to be much softer than the original feldspar. Here's another example. This is a granite that's been undergone Greisen alteration, so extreme sort of phyllic alteration, if you like. So quartz is okay, and the tabular feldspars have been replaced by cerussite, but they've maintained the texture of the granite. So that's a pseudomorph. And here's another example, but in this case we've got pink adulura replacing plagioclase, and we might have a vein. But this is mainly just around the selvage in this case. So out here it's mainly mildly cerussitized plagioclase. But closer up, the plagioclase has been placed by a K feldspar. Okay, veins, fairly self-obvious again. We had a look at this sample. But these are the pathways of the fluid, and we can have multiple generations of fluid pathways going through the rock, or they're related to different stress fields. And commonly you'll see the alteration selvage around the vein, which makes sense. That's the main controlling agent. So therefore it's commonly localized around those vein structures. Here's just some different example. There's a different timing relationship, like a fault. This one's offset this earlier vein by a later vein that's cut across it. So you guys are working through that stuff anyway. Just variations on a theme here. Breccias, so we can take it one step further and just completely fracture the rock by overpressuring a fluid or magma or faulting, and therefore we get angular clasts in a matrix, which is characteristic of pressure. We might have veins. In this case, we've got jasperoidal silica, is this red oxidized material from ferric iron. And so breccias can be quite common in that main conduit area of fluid flow. There's a variety of them. Don't worry too much about the details here. Just to know that you can get breccias in different environments. Technically, you can get sedimentary breccias, hydrothermal breccias, magmatic breccias. All a breccia means is angular clasts. So just take care in identifying the features of it to see if it's a hydrothermal thing or if it's a primary depositional environment. And faults is the other common one. So here's just a nice example. We have clasts, sedimentary rock, then we have sort of vein quartz material that's fragmented this host and infilled in different areas, and we get different alteration, in this case black chlorite, and here we have sphalerite. This is a volcanic rock, and we can see that most of the host rock would be something like this, so it's quite altered, but we have these areas where it's completely fragmented by these hydrothermal events. Yeah, more variations on the theme. Okay, replacement textures, or sometimes they're called coronae, where we see, essentially it's a partial pseudomorph, but we've seen a reaction between something to form something else around it. Okay, so it's a reaction texture or a replacement texture. So the mineral is in the process of replacing one another, or they form these corona around it. And commonly the original texture of the rock is preserved, which can be handy. Here's just an example of a pyrite replacing the edges of a lithic class, and there's some chlorite matrix. Overprinting texture, this is pretty similar to replacement textures really. We see these tourmaline rimming quartz here, which is a slightly distinct, we're changing the boron silicate is probably using the silica because boron's in the rock, but we're not getting a pure change of the quartz. The boron would require a lot of boron and other elements to come in to change that system. In this case we have stringers, or sort of aligned cases of chalcopyrite, and they're sort of forming in distinct structures that are probably overprinting, maybe bedding or an old vein feature that's then collapsed and then overprinted by another vein set. So here's just multiple generations of quartz, just pervasively altering this. Infill textures is probably the other important one. This is where you have like pores or vugs, and we're actually filling open space. So, this could be related to a breccia or the actual vein itself, because it creates a void, or other vesicles or vugs. So here's some lake quartz infilling a fragmented host. So this is really just the infill to this area that's been sort of brecciated. In this case, we see a nice layered growth based on it growing into spaces. All right, so just a little bit on phase diagrams. Like you guys, they look complicated. Sometimes they are, but generally they're a pretty good indicator of what is stable. So the whole basis of a phase diagram is around the idea of minimizing Gibbs free energy. So that's broadly the thermodynamic stability. So as most things in the environment, they want to have the lowest energy possible at that point. And so whatever's got the lowest Gibbs free energy at that point is stable. So in this case, we can look at pressure and temperature, and these are the aluminosilicates, kyanite, limonite, and andalusite. And depending on temperature and pressure, you have a different crystal form that is stable for Al2SiO5. And so this diagram is just telling you in this area it should be kyanite, in this area it should be limonite. Okay, but you can show other things, and you can look at imposed pressure and temperature is the most common one, but you could also look at changes in chemical content or composition. as well as what we call extensive variables, so things that are dependent on the amount of material, volume, enthalpy, entropy, redox, pH, CO2, etc. Okay, so they're quite powerful, and typically they have to be defined by a set of components, which can be a group of elements or potentially like a mineral. In this case, we're looking at aluminium and silica to assess just the aluminosilicates. And so there's other examples for these ones, like silica is quite common, carbon, calcite. But then we get into more complicated realms of phase diagrams, where we're now at the position where we can actually take something, in this case like a basalt, and go, what happens if we metamorphose or change this basalt at different pressures and temperatures? What mineral assemblages would we expect to form? So in this case, we don't need to get across the details of this, just to know these things are possible. To then go, well, if these rocks were at, say, 15 kilobars and 670 degrees, you know, we might get assemblages of hornblende, epidote, muscovite, pyroxene, rutile and garnet or something like that. So they're quite powerful, but we have to be aware of what goes in. So mostly we worry about pressure, temperature and composition, and that's what's been shown here. And phase, in this case, is any mineral, but also fluids. So water or CO2 or a mix of those, generally, the common occurrences. If you go back a level, the other case that we will commonly see is something called a petrogenetic grid. This is slightly distinct to a phase diagram. It shows common reactions that have been determined experimentally. So they might not be what is seen by the rock, but they could possibly be seen. In this case, we're just showing locations of common dehydration reactions. So for the purpose of here, things like chloride, sitting at about 550 there, amphibole much higher where we're getting melting, and fendite, which is a muscovite, at quite high temperatures. These are the sort of events where we lose water. Oh, and serpentine is also a handy one here at 500. So what's distinct about these diagrams is they're specific to a composition. So they're called complexly a pseudo-section, but that really just means we're taking a slice in a compositional space and looking at the pressure and temperature. So this is specific for a mid-ocean ridge basalt, and it tells us exactly what reactions we should expect or what mineral assemblages we should be able to see. And we can take different slices. It might not be composite, you know, we might want to look at how much water has an effect on this, or how volume has an effect on this, and things like that. We can look at different variables outside of pressure and temperature. So, in terms of hydrothermal mineral assemblages, in this case, this is a petrogenic grid. So we're looking at all, you know, classic reactions that have been identified experimentally. So, you know, here's an example of a propylitic alteration, you know, chloride epidote, hornblende plagioclase. So it's just largely a dehydration reaction or a hydration reaction, depending which way you go. Okay, so we need water to convert hornblende and plagioclase to chloride and epidote. If we go the other way, we lose water. So that's just a simple metamorphic reaction. But it's quite common for propylitic alteration. Another example here is a case of argillic, where we go from quartz and kyanite to quartz and an aluminosilicate. So we have to, in this case, we're above kyanite stability. And these change to a clay mineral, a mica. Oh yeah, it's a clay, sorry. Prophyllite at those conditions. And then here's another example of a phyllic, K feldspar muscovite. and they're just happening at different temperatures. And the phase diagram enables us to fingerprint what conditions these are forming at. So, like I said, we can look at things where we, instead of pressure and temperature, we might look at pressure and water in this case. So what effect do you have at a fixed temperature of adding water to the system? How will the mineral assemblage change? In this case, you usually lose things like pyroxene, form hornblende and epidote. But you could do, similarly, you could do something like a temperature composition diagram. It's much the same. And you're looking at various details. So they can answer complicated questions, just depends what we're looking at. And that's where we have to come up with different ideas. Here's a case where we're looking at pH, we could look at, what are these ones? Oxidation versus, I think, temperature. It's been cut off. You could also look at pH. And these are particularly important for looking at metallic species. We're looking at the form of cobalt here, or chromium, and how it is dependent on different variables. So this is a oxidation potential versus acidity for copper. So going this way, we're going more alkaline. This way, we can be more acidic and more oxidized. So we can go through, here's native copper, has a broad stability range from, essentially around 0 to more reduced conditions and fairly a broad spectrum of pH. But if you oxidize, you might get things like malachite. So these are common assemblages that you might find in the surface expression of an ore deposit. But if you reduce it, you might get chalcocite as a stable phase, and the same with if you change the pH at a fixed oxidation, you might get to gabellite. Okay, so they can be quite powerful. Just important to realise what we're sort of looking at. In this case, we're assuming a fixed pressure and temperature to then consider these. But equally, you could look at temperature versus pH, or temperature versus oxidation potential, etc. The final one I'll just briefly talk about is called an activity diagram. Activity is like a thermodynamic way of looking at the proportion of something. You might also see things in a true sense. An activity is technically you should be looking at a chemical potential. So a chemical potential, things move down gradients just like water, like osmosis or diffusion, and a chemical potential is just measuring those gradients to see how things will move. But activity is a similar scenario. So here we're looking at the activity of potassium versus hydrogen or versus sodium. So if you increase potassium or you increase sodium, we will stabilize different hydrothermal minerals. So we start with a clay. If you increase just potassium, you'll get muscovite, and if you increase it even further, you get hexalura. But if we increase sodium, we go to, instead of a potassic mica, we get a sodium mica called paragonite, and keep going, we get albite, so sodium plagioclase. And this is all just at fixed temperature, but if we think about an alteration example, we're likely to move in different manners across this diagram depending how that alteration system evolves. So they can be quite useful to show those changes and predict what might have happened. So that's all I really want to talk about. So we can leave that. Was there any questions?